Alrighty, so we're talking about historical astronomy. This is kind of an abbreviated version of this unit, so we can spend more time talking about things that are a little bit more fun. But historical astronomy is interesting and good to note because astronomy's been important to humans for almost as long as humans have had any kind of civilization. Ancient people used astronomy for a lot of different things that were just practical to their everyday life. For example, hunters and gatherers needed to know what time of year that herds of animals migrated or when different plants were going to be edible. And it's very easy to track the seasons through the stars or through the position of the sun. Agricultural civilizations needed to know when to plant and harvest crops. If you look at Egypt, there was a whole lot of importance placed on the star Sirius because it would appear right before, around the time that the Nile would flood, which was a huge part of their agricultural system. Seafaring cultures used the stars for navigational tools. For example, the Polynesians did a lot of navigating by stars, as well as the Vikings as well. And, nomadic people who needed to get together for ceremonies or discussions about different things, you could often plan annual meetings based on the positions of stars and planets because they track the seasons. And then, of course, a lot of other civilizations also, brought all this study of the stars that they did into their religious practices. But pretty much any ancient civilization had somebody that was tracking the stars because it was important for tracking the times of the year. Do you need a pencil?
No.
Okay.
I'll just look for my sharpener.
Okay. So we're gonna now move from the idea of what ancient peoples did into some historical things. And the two big historical models of the universe were the geocentric model and the heliocentric. And a major paradigm shift had to occur in science to switch between the two. And we started with the geocentric model of the universe, which was first popularized by Aristotle, who lived approximately 384 to 322 BCE. And again, he popularized the geocentric model of the universe. He kind of based it off the idea of perfect crystalline spheres. And that's what this diagram is kind of supposed to represent. And he had Earth as the immobile center of the universe, and everything else went around the Earth. Which it's kind of easy to see why someone might think of that as an initial idea, because from our perspective on Earth, it does kind of look like everything goes around us. And Aristotle was a philosopher, not a scientist, so he wasn't super concerned with gathering evidence to support his model. He just wanted something that he thought made logical sense. Now, the one thing that did support this model was a lack of stellar parallax being observed. And we'll talk a little bit about what that is. But that was the one piece of evidence that really supported the idea of a geocentric universe. So parallax is the change in the apparent position of an object due to the location of the observer. And no stellar parallax was observed in ancient times. So we can all kind of demonstrate what parallax is in a very simple process. If you hold your finger out in front of you and close one eye, and then open the other eye, you should notice, right, your finger appears to move position compared to the background. Right? That's what parallax is. So something that's nearer to your vision seems to change its position based on the position of the observer. So for stellar parallax, what you would think would happen is you should see nearby stars change their apparent position with farther away distant stars during the times of the year, right? So like when we're on one side of the sun in January, we should see a nearby star, closer to this side. But by the time the Earth makes it all the way around to the other side of the sun in July, that nearby star should appear to move to the other side. In ancient times, nobody was seeing this happen at all. Which means a couple of things. There's two possible ideas. First off, because if you don't observe stellar parallax, it might be because the stars are very, very far away. And simply that parallax, that change in position, was too small to measure at the time. The other option was the Earth didn't go around the sun. And so a lot of people who liked the idea of a geocentric universe used this as their main piece of evidence. If there's no stellar parallax, then the Earth can't be going around the sun. Now, this is something to always be careful of, because an absence of evidence is not the same as evidence of absence. Meaning, just because you don't observe something doesn't mean it doesn't exist. And this is the logical fallacy with people who are supporting the geocentric model of the universe throughout history. So, geocentric model, again, it was really popular, and a further philosopher, Ptolemy, who lived roughly 90 to 168 CE, was another big supporter of the geocentric model, and he was determined to be able to use this model to explain the motion of planets throughout the sky. Because over the course of the year, you see the different planets change their position in the sky. And they experience several different types of motion. They experience what we call prograde motion, where the planets seem to go forward across the sky with respect to the stars. But they also experience retrograde motion, where they appear to go backwards across the sky with respect to the background stars. And many, many planets experience this retrograde motion. Mars is probably the most obvious one, but Venus, Uranus, many of Saturn and Jupiter's moons, you will also see them do this back and forth movement in the sky if you watch carefully over time. But prograde motion means going forward, retrograde means going backwards. So this is kind of what we mean by a prograde and retrograde motion. So this kind of shows in the sky, Mars will appear to move forward, and then it'll move back a little bit, and then it'll move forward again throughout the year, depending on what time of year it is. And it's actually related to basically where Mars is in its orbit with comparison to where Earth is in its orbit. So it's not too difficult to think about when you're looking at a heliocentric model. However, that's not what Ptolemy was going for. He was basing this off of the geocentric model. And in a geocentric model, you need a lot more complexity to explain prograde and retrograde motion. So Ptolemy took on this idea of a wheels within wheels approach to explaining this back and forth movement of the planets. And he did this with epicycles and deferents. So a deferent was like a big circle that the planet was moving around in, kind of like a big gear. And then the epicycles were these smaller circles that kind of went around the deferent. So it was kind of like a big gear with like a little gear attached. And so that's how you got this back and forth motion. At least this is how it was explained in a geocentric model. And I think you guys have a diagram on your notes for this. Yes? Yes, you do. Okay. So in your notes, again, this big circle is called the deferent. So if we kind of draw it up here, right? So the big circle is the deferent, and the little circles that go around, like these, the little circles, these are the epicycles. And so Ptolemy came up with this really, really complex system to explain just how the planets kind of moved across the sky back and forth. And you know, it made logical sense. It seemed to kind of match with what was going on. However, it still didn't give accurate predictions of planetary motion. Another interesting thing about the geocentric model is that it requires a very small universe. Now, Ptolemy probably had the biggest estimation for a geocentric universe, and that was about roughly 50 million miles wide for the universe. Now, keep in mind, we measure galactic distances in light years. 1 light year is 6 trillion miles. So the idea that the universe is only 50 million miles wide is kind of crazy. It's incredibly small based on what we know nowadays. Now, why does it have to be so small? Because if you're dealing with a geocentric model of the universe, that means the Earth doesn't move, it stays still. But everything else moves around the Earth. And everything else would need to go around the Earth in a 24-hour period. Which means that if you're dealing with a universe the size of Ptolemy's, 50 million miles wide, the universe would need to be moving at 10 million miles per hour to get around in 24 hours. And the bigger the universe is, the faster it would have to move to get around the Earth in 24 hours. And we start to see how logically, even without the scientific evidence, this whole idea starts to fall apart a little bit. So a quick summary of the geocentric model. Again, main points: Earth is the center of the universe. That's what geocentric means, Earth-centered. The sun and planets orbit the Earth. Planetary motion is explained with epicycles and deferents, that kind of wheels within wheels idea. And the one big piece of evidence that supported the geocentric model was a lack of stellar parallax. No stellar parallax being observed. Oops, no, there we go. Now, it took a very long time for there to be a paradigm shift in science to move from a geocentric model of the universe to our next one, which is the heliocentric one. And it was proposed much, much earlier than it was adopted by the larger scientific community. And that's mainly because people liked the fact that they liked thinking that Earth was the center of the universe. They liked thinking that we were somehow extra, extra special. When in the grand scheme of things, that's just not the case, and it just doesn't make sense when you look at the evidence. Which brings us to the next main historical model, which is the heliocentric model. The heliocentric model was first proposed by Nicholas Copernicus, who lived from about 1473 to 1543. And he was the first person, not necessarily to have the idea that the sun could be the center of the universe instead, but he was the first person to publish about it. In a heliocentric model of the universe, the sun is the center of the universe. So it's still not an accurate model of the universe, but it gets closer. And Copernicus said that in this model, Earth's rotation is what accounts for the daily rotation of the stars. And the annual movements of the sun are caused by the Earth revolving around the sun. Oops. There we go. The other notable thing about Copernicus's model, as you can see in this picture, is that he represented the orbits of the planets as perfect circles. Early astronomers really had this fixation on making the universe, conform to perfect geometry. Which again brings us back to prograde and retrograde motion. This was one of the biggest things that Copernicus's model had going for it, is all of a sudden he could explain prograde and retrograde motion of the planets with far less complexity. Now, however, Copernicus still didn't have a perfectly accurate prediction for the motion of planets. So while he could simplify the process, he still couldn't completely get rid of epicycles because, again, he was basing the orbits of the planets off of perfect circles. But it now becomes much easier to talk about prograde and retrograde motion. When Earth is kind of lagging behind Mars in its orbit, because Mars is farther away, it looks like Mars goes forward in our sky. But as the Earth kind of catches up to it and starts to move ahead of Mars in its orbit, because again, Mars is farther away, then Mars looks like it goes backwards for a little bit before it starts moving forward again in our sky. So you don't need quite the level of complexity of wheels within wheels to explain prograde and retrograde motion. But again, Copernicus's model still couldn't give us really, really accurate predictions. Because again, perfectly circular orbits. Now, Galileo was one of the first people to really come up with some really, really solid evidence that supported the heliocentric model. Particularly the discovery of the moons of Jupiter. So Galileo discovered the 4 largest moons of Jupiter. And this kind of conclusively proved that, well, not everything goes around the Earth. You can clearly observe these other bodies orbiting Jupiter. He also discovered that Venus has phases similar to our moon. And the only way that Venus could kind of experience phases is if Venus was going around the sun so that its angle with the sun compared to Earth changed over time. But even though Galileo found this really conclusive evidence to help support the heliocentric model, it was still going to be a long time before it was fully accepted. Because again, people liked the idea that Earth was special and at the center of the universe. So here's kind of our quick summary of the heliocentric model. The sun is the center of the universe. The planets orbit the sun, and the moon orbits the Earth. Movements of the Earth the movement of the Earth causes the sun and the stars to appear to move across the sky. And the big pieces of evidence that support the heliocentric model were Galileo's discovery of the moons of Jupiter and phases of Venus. So that kind of wraps up the main historical models for the solar system. Now we want to talk about planetary motion. So we're going to be skipping ahead in time a little bit. And the main scientist who did a lot of the work with how to get accurate predictions of planetary motion was Johannes Kepler. But we can't really talk about Johannes Kepler without talking about Tycho Brahe, because Tycho Brahe was the guy who made the observations that gave Kepler the data to come up with his laws of planetary motion. Tycho Brahe was kind of like the last major astronomer before telescopes were heavily used. So he observed the supernova of 1572, which kind of made a big impact on him. He also was able to show that the comet of 1577 was beyond Earth's atmosphere, because previously people thought they were in the atmosphere. And he accumulated years of careful observations about the apparent motions of planets in the sky. Like, he had incredibly detailed catalogs of data and observations over a period of like 25 or more years. So the wealth of information that he gathered is incredible, especially considering he did all of it without a telescope. And he was actually able to detect stellar parallax, which was essentially the nail in the coffin for the geocentric model of the universe. And again, he was even able to detect stellar parallax without the aid of a telescope. What he essentially, because he was born as a really rich, like, Dutch nobleman, and he was a really quirky guy. He's got a very entertaining life story. Like, once when he was in school, he got into a duel with a guy over who was a better mathematician, and like got part of his nose cut off and wore like a prosthetic nose for the rest of his life. Yeah. He had a pet elk. He would throw wild, outrageous, lavish parties. And he convinced the king to let him have a whole island to set up his observatory on. And so again, he didn't have a telescope, but basically what he did is he made sure all of his other instruments were incredibly well calibrated. So we can kind of look at some of them here. So he used a quadrant to measure azimuth. So it's basically like you can point at something in the sky and then it'll tell you like what angle above the ground it is. And so he had very, very detailed quadrants made. He also had a great globe that he would use to track star positions. And then probably the other thing that was a real big one was the triangular sextant. His was huge, about 1.6 meters in radius. So a meter is like this long. So like roughly 1.5 of these wide. Typically a sextant is something you can hold in your hands. Okay. But because he was trying to measure very, very small changes in the sky over time, he wanted a very big one. He also had a revolving wooden quadrant, so one that would actually like rotate in a circle. Again, 1.6 meters in radius, and it had an accuracy of 32.3 seconds of arc based on reference stars. So remember, like, degrees of arc are divided into like 60 minutes in 1 degree, and then in 1 minute, 60 seconds. He could be accurate within roughly 30 seconds of arc across the sky in like the 1500s. So these were some really well-made instruments, and it was a pretty important a feat. But and so here's where Kepler comes in. So Tycho, again, he was a very colorful and very secretive character in general too. He almost never let anybody look at his observations. Now Kepler set up some like essentially like an apprenticeship with him, so he could start to use some of Tycho's observations. But Kepler really didn't get access to all of Tycho's data until he died. And it was kind of shady because Tycho's data was technically supposed to be inherited by his kids, but Kepler just took it all so that he could use it to create his 3 laws of planetary motion.
He died really young.
Yes, yes he did. But Kepler's laws of planetary motion were the first ones that could really very accurately predict the motion of planets, again, because they were based on over 25 years of data collected by Tycho. So his first law of planetary motion basically states that planets orbit around the sun in an ellipse, with the sun at one of the focus points. An ellipse is just like an elongated circle, kind of like an oval. And so, like, typically, right, like if you wanted to make a circle, right, like you can, put a string connected to a marker and you can just draw a circle. So that'll give you a circle. A radius is related to a circle. If you want an ellipse, you've got to have 2 points and then connected with 2 strings to your marker. And if you take that around, that'll give you an ellipse instead of a circle. And this was kind of the crucial thing that Copernicus's model was missing, because he was trying to do it with perfect circles. And so, like, how elongated an ellipse is based off of what we call eccentricity. So a circle has 0 eccentricity because it's a perfect circle. And then one that's just like a little bit oval shape, we'd say like moderately eccentric. And then like a really elongated oval, that would be highly eccentric. So again, eccentricity is a measure of how elongated the circle is. So is it just, like a little bit egg-shaped, or is it like really oval? And we can calculate eccentricity by this ratio. I would star that or circle it, something in your notes. Eccentricity is equal to the foci distance divided by the major axis. And in a minute, we'll label these different things on a diagram so you can kind of get a better idea of what they would be. But this is going to be important. We're going to be doing some of those calculations. And the foci are what we call the focus points of the ellipse. So basically, they're the little pins that you would use to make the oval shape. And for a planet, the sun is always at one of those focus points. And there isn't anything at the other focus point. The major axis is just the longest diameter of the ellipse. And then the semi-major axis is half the distance of the major axis. So the semi-major axis is kind of akin to the radius of a circle. All right, so now let's label these kind of things on our diagram so we can have a better, oh, there it is. So we can have a better idea of what they all mean. So once again, for a planet, the sun is one of your focus points. So let's make a dot, and this is going to represent the sun at one focus. But the sun is always at one of our focus points for the ellipse. And there's nothing at the other focus. So for a planet's orbit, one focus is the sun. There's just nothing at the other focus. again, this longest diameter here, that is the major axis. So that right there is the major axis. And then half of that is what we call the semi-major axis. So half of that is the semi-major axis. And then there's just two more things that we want to label on our diagram. And that is the terms perihelion and aphelion. And these are just terms that are used to describe different points in a planet's orbit. So perihelion should be over here. And perihelion is when a planet is closest in its orbit to the sun. So perihelion is closest to the sun. Aphelion is the opposite. Aphelion is when a planet is farthest away from the sun. So perihelion and aphelion are easy to remember. If you remember, aphelion means away. So aphelion, away from the sun. Are we good with this diagram then? Okay, I'll erase it and then we will continue onward. Okay, so we're gonna practice finding eccentricity here. Remembering that eccentricity of an ellipse So eccentricity is our foci distance divided by our major axis. So when we're reading this problem, we need to cue in on what the foci distance is and what the major axis is. So again, what is the eccentricity? Eccentricity is what we're looking for of an ellipse if it has a major axis of 18 centimeters, a minor of 6 centimeters, a semi-major of 9 centimeters, and a foci distance of 5 centimeters. A good trick anytime you're having to deal with some kind of word problem is to circle what the problem wants you to find and then underline what the important information is in the problem. So in this case, our important information is our foci distance of 5 centimeters and our major axis distance of 18 centimeters. And when we do 5 divided by 18, what do we get? Okay, so we'll call it 0.278. So 0.278 would be our eccentricity in this case. Now, like I said, there'll be a few problems like this on the, I believe on the Kepler Kepler Laws questions worksheet that we'll be doing on Wednesday. Are we good with this one then? Okay, I'll erase it and we will continue onward. All right, Kepler's second law states that as a planet moves around its orbit, it sweeps out equal areas in equal times. Which essentially what that means, equal areas in equal times, is that planets move faster when they're near the sun, and they move a little slower when they're away from the sun. And of course, we define aphelion and perihelion, like we talked about a little bit ago. Aphelion is when a planet is farthest away from the sun, and perihelion is when it is closest to the sun. So when a planet is close to the sun, it moves a lot quicker than it does when it's away from the sun. And this is related to gravitational forces between planets and the sun. And so anytime something gets closer to the sun because it experiences a greater gravitational attraction, the closer it is, it will speed up. And actually, NASA and other space agencies use this concept a lot to add speed to their spacecrafts. They will fly a spacecraft by a larger object so that that larger object will give it more speed due to gravitational forces and kind of fling it along towards its destination. It's called a gravity assist. Kepler's third law is a mathematical one. And it's one that we will be doing some calculations with. It basically states that there is a relationship, a mathematical relationship between the time it takes a planet to orbit the sun and how far away that planet is from the sun. And that relationship is p squared equals a cubed, where p is the period of revolution, how long it takes the planet to make one orbit around the sun, and a is the semi-major axis of its ellipse, essentially the radius for the circle, which essentially means like how far away that planet is from the sun. So, and for the planet, P, the orbital period, is measured in Earth years. So how long it takes the planet to orbit the sun will be measured in Earth years. And A, that semi-major axis, or the distance the planet is from the sun, is measured in AU, which are what we call astronomical units. Astronomical units are the main unit of measurement for anything within the solar system. And 1 AU, 1 astronomical unit, is defined as the distance from the Earth to the sun. So A for Earth is 1, and P for Earth is also 1. So let's kind of look through an example problem. So this example problem says, what time does it take Jupiter to revolve around the sun if Jupiter is 5.2 AU from the sun? So if we look at this, it's wanting us to find time. Time is the orbital period P. And they say that it's 5 AU from the sun. So that is our A in this problem. So we know our A is 5.2. We know that P squared equals A cubed. So we put 5.2 in for A, and you cube it, and you'll get 141. Then we have to get rid of the squared on our P. And to do that, we have to take the square root. So to undo a square, you take the square root. And the square root of 114 is about 11.9. And what that means is that it takes Jupiter about 11.9 years to complete one orbit of the sun, or to go once around the sun. Let's do a couple more problems like this together. I think we've got two listed in our note packet. So our first practice problem says, if a planet has an orbital period of 66 years, how far away is it from the sun? So it tells us orbital period, 66 years. How far away is it? So we're looking for A in this case. Well, we know p squared equals a cubed. In this case, we know what our p is, right? They told us our orbital period is 66 years. So I can plug 66 in for p. And then what is 66 squared going to come out to? $66 squared. Somebody do that real quick. So 4,356? Yeah. Okay. And so that's equal to our a cubed. Now, we have to get rid of the cubed on the a. Similar to undoing a square, you take a square root. Here we take a cube root. Now, if you have a scientific calculator, it's probably relatively easy to do a cube root. However, if you don't, the other way you can do it is raise it to the 1/3 power. So if we do this, like a cubed to the 1/3, that will cancel it out. So we can take 4,356 and raise it to the 1/3 power. And that's an easy way to take a cube root. It means the same thing as a cube root, it just might be easier if you don't have a scientific calculator. I would just make sure you put parentheses around everything. So I would put 4,356 in parentheses, and then use my caret button, and then put 1/3 in parentheses. And when you do that, you get like 16.3 equals A. What should my units for this be? If it's how far away? AU, right? So we should make sure we add in our units. AU. And that would be our answer for that first practice problem. Questions on this? Yes?
Did you say we have to find the square root of 66?
So you would have to square 66. And then once we get here, it's equal to a cubed. So then to undo the cube, we have to take a cube root or raise it to the 1/3 power. Both work. Other questions? All right, let's look at our second practice problem. It's similar to the example problem. It says if a planet is 16 AU from the sun, how long will it take to complete one orbit? So 16 AU, and we want to know how long to complete an orbit. Well, p squared is equal to a cubed. In this case, we are trying to find our p. We don't know what the orbital period is. We want to know how long. But we do know that our distance, our semi-major axis, is 16. So I can, p squared equals 16 cubed. So somebody do 16 cubed on their calculator for me. $4,096. So now we have p squared equals 4,096. Again, the last thing we have to do, if we want to know the orbital period, we have to undo our square, which means we need to take a square root. What is the square root of 4,096? Yes. 64. And again, if this is our orbital period, what should my units be? Years. So it should be 64 years as my final answer. Questions on this second practice problem? All right. All right, so to kind of wrap things up, Kepler's laws were very, very accurate at predicting planetary motion. Because he got rid of the idea that planets had to move in perfectly circular orbits, he was able to completely get rid of the idea of epicycles and explain planetary motion in a very clear, simple, concise way. And his predictions were far more accurate than anyone else previously. More accurate than Ptolemy and more accurate than Copernicus. And so we now have kind of a model where planets are going around the sun, but it's not in a perfect circle. They move in an ellipse.